welcome back. We're now going to start talking about Chapter 16, which is aldehydes. All right, then. That's terrible. Aldehydes and ketones. We got a taste of aldehydes and ketones in Chapter 15 when we reacted them with Grignard reagents and organolithium reagents. But first, before we get into reactions of aldehydes and ketones, let's review reactions we've seen in the past that make aldehydes and ketones. And then we'll look at nomenclature and we'll see how far we get. All right. Now, in terms of useful reactions to make aldehydes and ketones, I would not put ozonolysis on the list of things that comes to your mind first when you need an aldehyde or a ketone. It's really it's the opposite of a synthesis, isn't it, when you're breaking down a molecule? Now, it would be very well and good if you have a very cheap alkene that's readily available in nature and you do ozonolysis. If you need a starting material that's a simple aldehyde or ketone. And just a reminder here of what happens. You're going to cut the pi bond in half and you're going to get a carbonyl on each side. It was found in 6.3b using ozone followed by dimethyl sulfide. And you get an aldehyde on the left because this carbon has an H. So there's an H on the carbon with the carbonyl. That's an aldehyde. The other carbon has two carbons and it's going to become a carbonyl right here. It's a ketone. So it depends on what kind of carbon you start with here. You're going to get aldehydes and ketones. And that's a way to make aldehydes and ketones. Now this is much more useful synthetically. Remember, we're starting in the middle here. We learned how to make alkynes with groups on one side from acetylene. That's when we first introduced synthesis. Quick reminder, if we start with acetylene, and we hit it with something like potassium hydride, you could get acetylide. And then if you were real careful, you would have to be real careful on this one with a secondary carbon. This SN2, there's a lot of things that could go wrong here. You would have to be careful with your solvent and your temperature to avoid E2 reactions. But anyway, this is a review, and it's a lecture course. We don't worry about such trivial details as good yields and stuff in lecture. You'd make a carbon-carbon bond right here, and an isopropyl group over here, which is this species we're starting with right here. And then you could further react that species in the presence of mercury 2 sulfate and sulfuric acid in an aqueous environment. And if you remembered how this mechanism worked, the key intermediate was an enol right here with a double bond between two carbons and an alcohol, and then that underwent tautomerization to your more substituted carbonyl in the form of a ketone. If you required the carbonyl to be on the end, you would choose the hydroboration method using this special hydroboration reagent, reminder, Saya. Or if you want to remember it, you can use the Singer Sia. Sec isoamyl looks like this. And sec-isoamyl. We need two bulky groups attached to the boron, so we're avoiding multiple times this reacting with the pi bonds. And you get a key intermediate that has an OH on the end and a double bond between the two carbons, also called an enol, and it undergoes tautomerization to an aldehyde. Now, those were very useful reactions to make ketones and aldehydes. I really think you should have them ready for any test. All right, we saw another one. This one, I wouldn't be thinking of this first to make aldehydes and ketones, but it did make aldehydes and ketones. We took a vicinal diol. I can remind you how to make those. Vicinal diols. We used alkenes, and we can always make alkenes from things like alcohols. Use a little sulfuric acid and heat. Acid catalyzed dehydration. That's found in chapter 10. Little reminder here, this was chapter 4 and 7. This was chapter 7 and 9. SN2 reactions in chapter 9. Chapter 10, dehydration of alcohols. And then we can create our vicinal diol going back to chapter 6 using a special kind of osmium reagent, OSO4, and using some kind of a peroxide, like tert-butyl hydrogen peroxide, and you will make a vicinal diol, as we have in the 10.5 review in the box. Try not to cut off the box here. There. So I made this vicinal diol, and we treated that with sulfuric acid and heat, and we did another kind of dehydration, acid catalyzed dehydration with a rearrangement. You're saying, I don't see a rearrangement. All the carbons are the same, Dr. Whitaker. What are you talking about? Well, if you look carefully, the carbon on the end here had 2 hydrogens in the beginning, CH2, only 1 hydrogen here. Yes, that is another kind of rearrangement with when a hydrogen moves. So we made a cation here, the hydrogen moved there, and then you did an elimination to make the pi. I'm not going to test you on the pinnacle mechanism as a review mechanism. We get another product here. How did that one happen? Interesting question. Well, if you made a cation on the end, well, you wouldn't make a cation on the end, would you? Primary cations are illegal. So what would happen is you'd protonate the end alcohol. You'd have the hydrogen shift and kick it off. Notice there's 1 hydrogen here and there's no hydrogens here. It had to move. And you get a small amount of this because that one had to go by way of a no carbocation. This one went by way of a secondary carbocation. Too much review for a reaction you're not going to see again. So stop. I got it. All right, we also, this one you better review. Every test we use oxidation of alcohols without exception. We need to know how to make primary alcohols into aldehydes. PCC is the only thing that can do that. We need to know how to make secondary alcohols into ketones. PCC will also do that. You need to review that primary alcohols, if you use chromic acid, once again, this combination makes chromic acid, and the combination where you replace this chemical with K2Cr2O7 also makes chromic acid. You will get a primary alcohol becoming a carboxylic acid. I don't think you want that in the chapter where we're trying to make aldehydes and ketones. But secondary alcohols, they don't care which chromium you use, whether it's pyridinium chlorochromate or if it's, chromic acid, you're going to get a ketone either way. And I don't believe we're going to do any periodic acid oxidations this chapter, but I do want to remind you, they also made aldehydes and ketones. It's kind of reminiscent of the ozonolysis if you look at it. This molecule is breaking down, diols break down to things that look like ozonolysis products. And there was a periodate ester in that one. And we made an aldehyde on the end and an aldehyde here because both of these carbons had at least one H, so aldehydes. Definitely review all the chromium reactions. That's these on the left side. Periodic acid, you probably won't see that again. So we've seen reactions that make aldehydes and ketones. We need to definitely have those in mind when we're studying a chapter that's about aldehydes and ketones. All right, so we're going to do aldehyde and ketone nomenclature. This is a new thing. And we're having common names and UPAC names, and you never know which one I'm going to give you on a test and ask you to draw the molecule. So we have to be comfortable with both methods for naming aldehydes and ketones. Common name or UPAC names always make sense. Meth means one carbon. There's one carbon, and it's an aldehyde because it ends with al. All these end with al, except for this one. We'll talk about that shortly. Methanol, ethanol. We need to know that the form prefix, and this is not new, but you may have forgotten, what does form as a prefix mean? Well, I'm going to get, I lost everything. Form as a prefix really is a carbon with a bond to hydrogen. Most often, that's a carbonyl. The reason I said most often is we saw chloroform earlier today. And it had just the H and the C. The single H with the C. So although it doesn't fit the normal chloroform we're using, where there's a carbonyl, its origins are based on the hydrogen and carbon. But our normal form group, formaldehyde, formic acid, formamide, FORM, is usually H-carbonyl. And our acete, which is even a more popular prefix, see form and acete very commonly in organic chemistry. That's not an H attached to the carbonyl. It's a CH3 attached to the carbonyl. And then attached to some entity, acete. And we saw even an exception to that back in chapter 7, where we had CH3 attached to a C, and, well, not really. I don't want to get too much into it. We call that acetylene. And we went into the story of how it got such a crazy name. And it has to do with the reaction that we just reviewed. When you do a hydration reaction on that, you do actually get acetaldehyde, which has the traditional CH3 carbonyl. So that's how it got its name, even though it doesn't look like an acete at all. So there's acetaldehyde. There's benzaldehyde, very common name. Benzene carbaldehyde. This is a new thing. Benzene carbaldehyde. When do we use carbaldehyde? I think that deserves its own explanation. Carbaldehyde is used when there is an aldehyde sticking off of a ring. And that deserves its own little comment. And make it stand out a little bit. And get a highlighter on that. Okay, and look, we have a phenyl with an aldehyde. Okay, in fact, let's see how we've been paying attention here. Let's rename vanillin. It's got two names. Vanilin's that one. I don't even expect you to memorize that. You should be able to do this. And that name's based on this molecule, isn't it? There's a phenyl attached to an aldehyde. Please call that benzaldehyde as your first choice because that's its common name. I have some lab students who will verify that for you. They've already used benzaldehyde once this semester. So this has benzaldehyde in it, and it has a methoxy on carbon 3. Methoxy, go back to chapter 11, we could name ether groups as alkoxy groups, methoxy. It's on carbon 3 because if you name it benzaldehyde, the numbering goes like this. 1, 2, 3, and there's a hydroxy on 4. So we'll do an alternate name for vanillin. It'll be a little awkward because we're going to use the carbaldehyde naming. So we're going to call it benzene carbaldehyde instead of benzaldehyde. And it follows the same pattern after that. It's got a hydroxy on 4. And hydroxy. That's an RO. Not very good looking, but hydroxy 3-methoxy. Oh boy. Benzene carbaldehyde. You say that to a chemist and he's going to have to think a bit. And he says, don't you mean vanillin? Or don't you mean 4-hydroxy 3-methoxy benzaldehyde? This is just awkward, but perfectly acceptable. Okay, moving on. Oh, cinnamon. Some people like cinnamon better than vanilla. I had some cinnamaldehyde on my French toast this morning. And what is that? It's got a phenyl and then a vinyl and then an aldehyde if you look at it. And the naming here, the UPAC, if we needed to do the numbering, propenal is right here. Why is there no number on the ene? This is a good question. Why is there no number on the ene? Well, you really can't put the double bond there. That would be a new functional group with a double bond on the same carbon as the aldehyde. A functional group we're not even going to talk about in this course. It's called a ketene. Let's not go there. So it has to be between carbons 2 and 3. And what else do we have? We have a phenyl on 3. And what's the E mean? Means the high priority group on this side of the alkene goes down, and the high priority on this side of the alkene goes up. They're on opposite sides. That's E. You could also call this trans because it's a simple alkene. And in simple alkenes, trans and E are the same. What do I mean by simple alkene? It's an alkene that has one group on the left, one group on the right. If there are more than one group on either side, it's not a simple alkene. Please don't use cis and trans. That's a chapter 5 review item if that went a little fast. Okay, so we have aldehydes. We will get some practice naming our own aldehydes and ketones on the next page. Just doing the intro here. Ketones, well, it's got the acete prefix on the first one here. It does have a CH3 attached to a carbonyl like this acete. And then it ends with -one, so it's clearly not an aldehyde. Well, what do you have to do to make it into a ketone? You've already covered the CH3 and the carbon with the acete. You need at least one more carbon or else you don't have a ketone. So acetone has the minimum one more carbon. Oh, look at this common naming system underneath. Dimethyl ketone. Where have we seen stuff like that before? No, that's not a ketone. Okay. So the ketone part's covered by that, and the ether part is covered by that. And just name the groups on each side of the highlighter. I like that. It's a simple system. I like simple things sometimes. Propanone, well, that one kind of explains itself, doesn't it? 3-carbon ketone. You don't have to tell me where the ketone is. It has to be in the middle or else it's not a ketone. Okay. Butenone. Once again, there's no number for the ene. Well, if you tried to put the ene here, you'd have an octet violation on the carbonyl. So it can't be anywhere but there. Similar story here, octet violation if you put the ene there. So butenone, he doesn't need a 2 for the ene, or 3, sorry. 1, 2, 3. There's some rule I haven't told you about yet about priorities of aldehydes and ketones. It's coming up, wait for it. We can also call it methyl vinyl ketone. I've got on one side, I've got the methyl group. It's on the right side. On the other, I have a vinyl group. And carvone, I don't expect, if I said carvone on a test and asked you to draw it, that would just be unfair. Okay? So if I drew this picture, you should give me this name. Does the name of the group isopropenyl make sense? It's got the V, but it's got a double bond as well. So it's an not an isopropyl, it's an isopropenyl. You got an E here. Oops, highlighter. Got an ene here. And that's an ene here. And it's got a methyl here and a double bond here. And where's the -one? The numbering. It's time to talk about priorities of aldehydes and ketones. They have higher priority than anything you've seen so far. That's what made that carbon number 1 up there. Oh, can I draw a 5? It's very small. So 1, 2, 3, 4, 5. Name says isopropenyls on 5, methyls on 2, cyclohex 2-ene. You do have to tell me where the double bond is this time. It's between 2 and 3. That's what the 2's for. You do not need to tell me where the -one is because ketones and aldehydes have high priorities. In a ring, it's understood if you say cyclohexone, any kind of cyclohexanone, that's carbon number 1, the carbonyl. All right, so we have a new rule. Aldehydes and ketones have high priorities. So this would be carbon number 1 on this one. This would be carbon 2. And muscone, found from a gland in musk ox, it's a fragrance. It's a musk. And they named that actual animal because he gave us the musk. Sad story. Getting stuff from animals, I'm not a big fan. It's UPAC name. That's the one I would expect on the test. I don't expect you to say, hey, that's muscone, or I give you the name muscone and you draw it. No, I'm not. That's not good. You should be able to give me that name. All right, so we have aldehydes and ketones with high priority, and we're going to do some examples. Carbaldehyde was a new thing. Let's just start with a simple one. I have a molecule here with a carbonyl in the middle of a chain, making it what? An aldehyde or a ketone? Can't be an aldehyde. That would be the end of the chain. It's got to be a ketone. Carbons on each side. It's ketone. Knowing your new rules. Where's carbon 1 in this chain? You guessed it. The left side. Ketones are more important than groups. 5, 6, 8. So we have 6-methyl. Now you've got to tell me where the ketone is. It's an octanone. But you need to tell me where the ketone is. It could be a ketone if the carbonyl was here, 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 or here. It's on carbon 3. And another way to name that looks, let's see, is this going to work for me? I didn't think so. I think I'm going to have the same problem all the way through. Start from the beginning. 6-methyl. You can put the oct first. It's an octan because there's no double bonds. And sneak the 3 right before the own. I think this is what we did with alkenes and alkynes as well. Both are perfectly acceptable names. Good start. How about a simple aldehyde? And let's put ethyl there. Are we starting from the right or the left on this one? And you guessed it, from the right, because the aldehyde's more important than this ethyl group on 4. So it's a hex and al. Oh, I have my answer here. Okay, it's a hex and al. You're saying, where is the number for the aldehyde? Are you saying that? That's a good question. You do not need a number ever for the aldehyde. The aldehyde must be at the end of the chain, or else it's not an aldehyde. And you have to tell me there's a methyl on, an ethyl on 4. For ethyl, hex, and al. And let's do one that has both an aldehyde and a ketone. Ooh. Pen's off. We haven't seen a stereo center all day. Actually, in the review we did. Okay. All right. What's more important, the aldehyde or the ketone? That's a good question. We haven't talked about that. They're very similar in priority, the aldehyde and the ketone. Almost co-equal. The good people at UPAC, their argument is this, and I like this argument. An aldehyde marks the end of a chain. Ketones, they can be somewhere in the chain. So anything that tells us where the end of a chain is, let's give it a slightly higher priority. In the other group, because it's got a lower priority, and you can't end a name with two functional groups, we need a way to say there's a ketone as a group on carbon 4. So we're going to have a new thing coming up. If you want to tell me there's a carbonyl on any position of a chain, it is acceptable to use this new thing, this new group name called oxo. So if you see number followed by OXO, it says one thing. That carbon number is a carbonyl. And alphabetically, it's going to go after fluoro. It's just a new group. Nothing spectacular. 5 fluoro. Leave a little room for a stereo center. And 4 oxo. So we're not going to end with one, are we? We've already covered the carbonyl. That's the ketone. And we're going to say it's heptanal. Oh, we don't need a dash. There's no number here. Can I make that into an H? Not really. Still learning my new pen. And that stereo center is S. We have a 1 for a fluorine. We have a 2 for a carbon that has an oxygen. Don't even need to know it had 2 bonds to oxygen, because the next one has no bonds to oxygen. So it's S. Counterclockwise, 1, 2, 3. And there you go. We have a new thing, oxo. Let's do one that has what you think would have to be an oxo again. How we doing? I don't know. We could have a short 5th segment or a early ending. I know what you're voting for. We've got a ketone. Throw one of those groups in there. And sometimes our aldehydes are drawn like that. Ooh. Is that not an aldehyde sticking off of a ring? How do you name those? Carbaldehyde is used when there's an aldehyde sticking off of a ring. Sorry, there's no space there. So this is going to end with carbaldehyde no matter what we do. Maybe we'll put it here. All right, so I'm pretty flexible on this molecule. The end is carbaldehyde. Carbaldehyde. We're going to do it 2 ways, and both are going to be fine. You can name this molecule that's not the carbaldehyde. You can name every part of it that's not the carbaldehyde as if the carbaldehyde wasn't there, and then add it as a group at the end. If you choose to do that, then what you have is a cyclohexanone. And yeah, you can have the ketone in the name because these are 2 separate words. I didn't tell you that. Yes, there's a space there. And it's got a group on carbon 3. If you go cyclohexanone, carbon 1 is there. I know, I just finished telling you aldehydes were more important than ketones, didn't I? But this is one where we have the aldehyde off of a ring. And this one, you're going to say 3-carbaldehyde. I want to make sure you know there's a gap here. 3-carbaldehyde. And there's a trifluoromethyl group on 3. Oh yeah, let's get that in there. And oh boy, a double switch is, I'm just throwing stuff at you. It looks like this is our last segment, doesn't it? What has a higher priority? A C with a bond to F? Notice I said 1 bond to F because that's going to be the decision maker. A C with 1 bond to F or a C with 1 bond to O? F, 19. O, 16. We're talking molecular weights here, aren't we? So I didn't even get to the second F to break the tie. And the CH2 that goes to a C with a bond to O, that 3 is going to be in the way of my name, isn't it? And 4 is here. Now, if you connect 1, 2, and 3, you got a 50% chance of being right. This is the time where a double switch is needed for a 100% chance. What am I doing now? I'm copying the stereo center. I'm putting the 4 on the dash, which means I switched it with the 2. That's a single switch. Don't ever just do a single switch. Switch the other 2 and you're back to the original stereo center. Oops, I'm switching with a 3, not a 2. And it's S. If you had done 1, 2, 3 here, you would have got R. You had a 50% chance. Our other name here, and we'll go with, let's see, what are we going to go with? Purple. You can say, Dr. Whitaker told us aldehydes are the most important functional group. They're even higher than ketones. I'm going to go with that rule, and I'm going to say that's carbon 1, and that makes this carbon 2. It's getting messy here, isn't it? And that's carbon 3. And I don't know. The rest of the name is the same. The numbers change. 1 trifluoromethyl, 1 carbaldehyde. Cyclohexanone. This time you do have to say this. Oh, that's purple. And 1 carbaldehyde. Oh, yeah. Is a separate word still. And both names would receive full credit on the test. If you say cyclohexanone is the priority, I don't need a number for the own. It's understood to be 1. And I knew you did that when I looked ahead at your name here and you said, oh, the aldehyde's not on carbon 1, it's on 3. Okay, so I would give you full credit for either one.
Doctor, I have a question.
Yes, a good way to finish is a nice question.
So what would happen if I said the name was S, and then I go by 1 as for ketone, and then 2, 3 on the C with the 3 fluorine, and then 4 as the C with the
Oh, wait.
aldehyde.
You said 2 for the ketone? Well, the ketone's 2 away from that.
Yes, so what would happen if I said the name as S?
Yeah.
Then 3 carboaldehyde, and then 3
Oh, that has to be at the end, by the way. If you
Why?
use that's the rule. That carbaldehyde is a separate word at the end. That's the only way you can ever use it. That's just
So
a rule.
if we use the word benzaldehyde, is it going to be the
No,
same thing?
benzaldehyde is like a molecule, and then you're putting groups on it. When you said the word benzaldehyde, you automatically started with this nucleus here with the aldehyde attached to benzene, and you made this carbon 1 by saying the word benzaldehyde.
Okay.
Aldehyde is a common name. Okay, so as soon as you say benzaldehyde, you've covered this ring and the aldehyde. So that has to be 1, and then you're going like this. But you can't use benzaldehyde over here because it's a cyclohexane. There's no common name for that. I don't know if I answered your question.
Yes, thank you.
Oh, I did. Okay. And if you're still confused or having an issue with that, email me, because if you're confused, chances are other people are too, and I could put a comment in the video or in the posting for the notes. All right, everybody, that is the end of today's lecture, and I hope you have a great weekend. You're going to try to finish. 16 is a big chapter. It's our biggest chapter of the semester, but try to finish reading it before Monday, because we're coming up on getting ready for review day. And my goal this weekend is to get your problem set done, even though you're not going to see it for a little bit after that. But you should be getting ready to get to that test material as soon as you can. So I'm going to bid you farewell and have a great weekend.